So in 2016, I read an article in Nature that said fast radio bursts, or FRBs, were the most perplexing mystery in astronomy. And since then, there's been a lot of progress. But a new headline caught my attention, claiming that a recent study has only deepened the mystery. So, with me to clear up what's going on, I have one of the authors of the study, Calvin Leung, NASA Einstein Fellow at UC Berkeley. So, welcome, Calvin.
Thanks for having me, Phil. And I'm really excited to talk about our new results with you.
So, why don't we start with what is an FRB and how were they first discovered?
Yeah, so an FRB, it stands for fast radio burst. And as its name implies, we basically don't understand what these things are, but we do know that they're really fast flashes of radio light. And we know that they come from outside our Milky Way. And so that's not tens, not hundreds or thousands of light years away, but potentially millions or billions. And so, a big question in astrophysics, which has perplexed radio astronomers for the last decade, is what could possibly be causing these extremely powerful, yet extremely brief flashes of radio light?
So, yeah, what are the main theories of what causes them?
Yeah, so some of the main theories nowadays, most theories involve neutron stars. Neutron stars are basically enormous atoms. We normally think of atoms as neutrons and protons surrounded by electrons going around. Neutron stars are enormous macroscopic hunks of, they're basically giant balls of neutrons, which are gravitationally bound instead of bound with the strong nuclear force, as we know in our normal atoms that we know and love. Now, these enormous neutron stars, they weigh about as much as our sun. However, because they're made of nuclear matter, they're extremely dense. They're something like 10 kilometers on a side, even though they have an enormous amount of mass. And that gives them an incredible amount of energy, which they can unleash in many different ways, from producing things like X-ray flares, which we've seen, from producing regular radio pulses. And so we don't think it's a huge stretch of the imagination that they could potentially produce these fast radio bursts that we see as well. We have really strong evidence that magnetars can produce these strong radio pulses. One of the strongest pieces of evidence we have so far is that there is a magnetar in our own Milky Way. This is SGR.
Let me just interrupt. What's the difference in between a magnetar and a neutron star?
Oh, I'm sorry. So a regular neutron star has a much weaker magnetic field than magnetars. So the idea here is that in the same way that electrons whiz around the nucleus, in a neutron star, you might have regular protons and electrons hanging out as well, even though their name is neutron star. A small fraction of the nucleons near the surface of a neutron star can potentially turn into protons and electrons. And the idea is that the presence of those charged particles can create very strong magnetic fields, which then turn a regular neutron star into something that has a magnetic field maybe 10 or 100 times more powerful than you would expect in an ordinary neutron star. And so whereas ordinary neutron stars might have magnetic fields of maybe a million times what you see in a hospital, like an MRI magnet, which has a strength of about 1 Tesla, magnetars can be hundreds or thousands of times more powerful. And so they're really commonly invoked as theories to explain some of the strangest phenomena that we see out in the universe.
Right, but then why this sudden flash? Because it is quite a sudden pulse, right? Hence the name fast radio bursts. Is that right?
Yeah, that's a really good insight. The sudden millisecond duration of these pulses makes us think that it's something really small creating the pulse. It can't be something big because you would need to coordinate sort of the entire surface of some massive star to radiate all of its energy in a millisecond. And the only way you can do that coordination is over a very, very compact region of space-time. And so the idea is, how do you get such a huge amount of energy packed in such a small amount of space? A really natural theory is a neutron star or a magnetar.
Right. And then how does it compare to, let's say, a gamma ray burst?
Yeah, gamma ray bursts are extremely energetic as well. They are typically a lot longer than FRBs, which is why we call them fast. Gamma ray bursts. Now, I'm no expert. I think that they last somewhere between a second and minutes, whereas fast radio bursts have been seen on timescales as short as hundreds of nanoseconds. So the difference in timescale is immense, even though we refer to both kinds of phenomena as flashes.
Right. Okay. So you've got these very fast flashes coming from these neutron stars that become like a magnetar. But it's been reported that you've discovered a new type of FRB that sort of may undermine our theories of FRB formation, or at least they're quite surprising on the current theories. That's the news story. So what has actually been discovered, and what are the possible implications?
Yeah, that's a great question. To understand why our new discovery puts existing theories into question, why it challenges existing theories, we sort of have to go back and see what we know about these FRBs. So in 2020, one massive breakthrough in the field came when our telescope, called the Canadian Hydrogen Intensity Mapping Experiment, when we discovered a giant radio burst from a magnetar in our own Milky Way. And this was remarkable because we knew of that source since the 1990s, and we had known it to be an X-ray emitting magnetar. And so seeing X-ray emission is sort of a smoking gun that we have a magnetar. And we knew that that source began to produce X-rays in early 2020. So we had our eye on it, that it could potentially produce a radio burst. And in April 2020, that's exactly what happened. We saw a radio burst coming from this source. It was immensely bright because the galactic magnetar was so close by to us. And from that conclusion, we were suddenly given evidence that magnetars in our own Milky Way could produce extremely powerful radio bursts. So then, whereas once it was a large stretch of the imagination that we could use extragalactic magnetars to produce these FRBs at extremely great distances, suddenly we had an example in our own backyard, in our own Milky Way, of a magnetar that was doing something really, really similar to what we were seeing in these cosmologically distant FRBs. And so suddenly all the papers began to say, oh, FRBs, they're coming from magnetars. And actually, since we knew the age of that magnetar, we know that it's something like 10,000 years old. And now, while that might sound like a huge amount of time, actually in timescales relevant to astrophysics and cosmology, 10,000 years is like the blink of an eye. It's quite literally, maybe it's something like a year when referred to the human lifespan. Whereas some of these massive stars can live for 10 million years, 10,000 years, it's really not much. And so then the idea was that, well, you have this young magnetar, it's newly born, it's just 10,000 years old, and it's producing these fast radio bursts. And so then, coupled with other indirect evidence from other channels, the field began to think that it was really young magnetars that were driving the formation of FRBs. Which now brings me to our most recent discovery of a FRB in the outskirts of a massive elliptical galaxy. Now, there's a lot going on here. So first, it's an FRB discovered in the outskirts of a galaxy, which in itself is sort of strange, right? You would expect magnetars, like stars, to be formed sort of at the centers of galaxies, where you have things like the disk. Like if you look at pictures of our own Milky Way, you'll see that at the center there's a beautiful spiral, and there's kind of nothing going on beyond a certain radius. Now, the FRB that we saw was one of the most offset from its center of light that we've seen to date. And so this calls into question, how did a magnetar get all the way out there where it seems like no other stars are hanging out? We know magnetars to like the centers of their galaxies. And so the fact that it's in the outskirts was already surprising. The other half to the discovery was that not only was it in the outskirts of a galaxy, the galaxy was also an elliptical galaxy. Now, galaxies come in two flavors. Some are spirals and some are ellipticals. It turns out that elliptical galaxies tend to have much older stars than spiral galaxies. So the mystery only gets deeper when you say, well, not only is this FRB coming from the outskirts of a galaxy, it's also a red and dead galaxy that hasn't formed stars in potentially billions of years. So how do you get a young magnetar, something that should have recently been born, in a red and dead galaxy, and all the way in the outskirts where it really shouldn't be hanging out? And that's
So this
why,
seems. Oh,
yeah, go
sorry.
ahead.
This seems pretty crazy. Like that. You had discussions with theorists, and like, how could this possibly happen?
Yeah, totally. So I'm gonna we have been discussing amongst ourselves some theories of what this source could be. One potential possibility is that it's actually a neutron star in a globular cluster. Now, globular clusters are groups of stars. They are long dead, but we also know from the globular clusters in our Milky Way that they can have tens or hundreds of neutron stars. They are sort of like stellar graveyards. When you have lots of young stars forming, they live their lives and they exhaust their nuclear fuel and they die, and they sort of coalesce into these globular clusters in our own Milky Way. And we know globular clusters to host exotic stellar remnants like white dwarfs, neutron stars, as well as black holes. And globular clusters in our own Milky Way are among the oldest substructures within our own galaxy. So it's not a real stretch of the imagination to think that this massive elliptical galaxy could host tens or hundreds of globular clusters, and it might just be that these globular clusters are hanging out in the outskirts of these galaxies. Um, since we see globular clusters hanging out at the outskirts of our own Milky Way. So my money is on a globular cluster. We actually have a James Webb Cycle 4 proposal in, which will allow us to potentially discover a globular cluster and go really, really deep on that field to see if there is something there that could explain the presence of this FRB.
And are there any other ideas? Anything exotic and wacky, or is
Yeah,
that
yeah.
where everyone's betting?
I love thinking about these exotic theories. There used to be so many of them. There was actually a day in very early on in the field of FRBs when there were more theories than sources discovered, and I think that's really exciting. And the existence of this source maybe should make us go back and revisit. Well, what were some of the more exotic theories that we ruled out that could potentially explore or that could potentially explain the nature of this new source we've discovered? It could be that there are multiple formation channels, that some FRBs come from young magnetars, others come from old magnetars. But I think the fact that we're seeing such a puzzling diversity indicates that we shouldn't throw away theories just because it doesn't explain the full population. I think you really need multiple formation channels in order to explain the broad diversity we see, not just in this source on the outskirts of an elliptical galaxy, but also other sources in the literature which have popped up and which have also posed puzzles for us to discover. Yeah.
Right. And what were some of the more exotic explanations? I think I remember like exploding black holes or something like that.
Yeah.
I can't remember all of the exotic solutions there were. Do you recall some of the more interesting ones?
Yeah, some of them had really exciting names like axions, cosmic strings. There was one even called quark nuggets. Now I'm no particle physicist, but that sounds kind of tasty. And it's just very hard for me to say, which one of these there are because they sort of they I think they were all a bit more speculative than the magnetar theory, especially when
Right.
we discovered that giant flare from a magnetar
Right.
in our own Milky Way. So we had
Right.
sort of discarded those maybe a little prematurely, and they should be revisited in light of this
Right.
new discovery.
Right. So tell us a little bit about the instrumentation. Like the new telescope is CHIMES, not quite so new now, but tell us a little bit about CHIMES and these outriggers. What are they, and how have they improved FRB science?
Yeah. So CHIME initially was a very strange telescope. It was designed to map 21 centimeter emission over the night sky. And this was a technique proposed in the early 2000s. And telescopes are just coming online, which have the ability to use this intensity mapping technique in order to map a huge amount of the sky at once. Now, it turns out that seeing a large amount of sky at once is exactly what you need to detect a lot of FRBs. And so um, CHIME got CHIME also, in addition to being a world-leading detector for 21 centimeter radio emission, is also the world's most efficient telescope at discovering FRBs. We discover FRBs at a rate something like 10 times all of our competitors combined. And that was true back in 2018 when we turned on. It's still true in 2024, even with even as technology from GPUs and software-defined radio continues to improve. And so CHIME is an extremely powerful instrument. However, only recently have we been able to add to it the ability to pinpoint our discoveries. And so you can think of CHIME as sort of a nearsighted telescope. It can see flashes, but it can't really pinpoint them very well.
But when you say pinpoint, do you mean get their location?
Exactly. Yeah. We've just completed a massive upgrade of CHIME that adds something like 3 new cylinders. These are sort of cylindrical reflectors, and what these allow is for us to pinpoint all of these discoveries. And so, whereas CHIME once was extremely nearsighted, couldn't really figure out where these flashes are coming from in the sky, now it has the ability to triangulate its discoveries using very long baseline interferometry. This is a technique that people use to image black holes, to make some of the sharpest images in the universe. And now we're using that to pinpoint these mysterious fast radio bursts in order to figure out where they come from.
Right. So now what about FRBs as probes of fundamental physics and cosmology? Because this sounds like really exciting. It's not just, well, what are these FRBs, but they could also help us like explore deeper into the universe. How might they do that?
Yeah, I'm so glad you asked about that, Phil. I think that's a really fascinating aspect of the FRB question. And it sort of broadens the field from high energy astrophysics, and it also ties into cosmology as well. And so that's one of my favorite aspects of thinking about FRBs. So it turns out that FRBs give us a way to measure the large scale structure of the universe. And you can think of them sort of as sonar pings. And so, whereas submarines send out sonar pings to learn about the seabed, it's possible to use these FRBs as radar pings coming from very far out of the universe that traces out the structure of the universe on their way to Earth. And so it turns out that this gives FRBs a really natural place in cosmology. Similar to things like the cosmic microwave background, which sort of traces out the structure as that ancient light travels through the entire universe on the way to Earth.
Right. And actually, theories of the very early universe, you might think are very separated from these high energy astrophysics sources. But if you can map out the large scale structure, shouldn't that help us differentiate between different theories of the early universe? Because wouldn't they make different predictions about large scale structure?
Yeah, absolutely. So a lot of these, a lot of theories of, a lot of theories talking about with a lot of theories about early universe physics make different predictions for what should happen at late times on really small scales. Now, a major obstacle in actually testing those predictions is our ability to understand those really small scales, because on small scales, you also have messy processes like active galactic nuclei, like these black holes at the centers of galaxies. They spew out gas and they sort of contaminate the pristine cosmological predictions. So if you actually want to make measurements at small scales for cosmology, it turns out that you have to be able to independently measure the gas density in and around galaxies. And so this has been a major obstacle in our ability to test things like different alternate theories for early universe inflation using the large scale structure. Why I'm really excited about FRBs is that they give us an independent handle on exactly what's happening on small scales due to things like AGN feedback. So the idea is you have one more known, and then you can sort of use that, turn that around in order to ask the questions that we're really, really interested in what does the clustering of things like dark matter look like on really small scales.
And are there any other mysteries that they can help with, like dark matter or dark energy, anything like that?
Yeah, so in a far future, I eventually one day want to design and build a telescope that could measure lensed FRBs. And the idea here is when I say lens, I don't mean lensed with something like my glasses. I mean that there are, every now and then, you'll have a source in the foreground and a source in the background. And the source in the foreground will it will gravitationally bend the light from that background source, and so that you see multiple copies of that source. Now, if we were to observe this in FRBs, it could lead to the most precise measurements of the expansion rate of the universe that we have. This is
And
a
that
far
could
off
help
future.
solve the Hubble tension, right? That's this
Exactly.
tension between different ways to measure the expansion rate of the universe. And people are thinking, wow, they don't agree. Could this be a sign of new physics, or is it just a measurement error? And so presumably this could actually help resolve that tension.
Exactly. Yeah, the Hubble tension is one of the biggest mysteries in cosmology. We don't have a great idea of exactly where the discrepancy is. And I will say that this has led to some heated debates in the cosmology community. And it would be so wonderful if we could one day bring online a new probe that could sort of act as a tiebreaker. It's independent from everything we've done so far, and because it relies on just gravity, there's no complicated astrophysical modeling involved. We think we understand gravity really well, and so if we were able to use gravitational lensing in order to measure the Hubble constant using things like FRBs, then this would be an amazing breakthrough in cosmology.
Wow, that's super exciting. So are there any other things looking to the future for FRB physics that you're excited about, or where do you think we'll be in sort of 10, 20 years from now?
It's really hard to say because this is a field that's really young and it also moves really, really fast. Whereas, 3 or 4 years ago, we had no idea where these things came from. We're now saying, well, some of them come from young magnetars, some of them potentially come from old sources. That I would say is a huge leap forward in just the span of a few years. There are next generation telescopes coming online, which will improve on discoveries and breakthroughs like we've been able to make with CHIME by tenfold. There are two telescopes at least coming online, which will have discovery rates of something like 10,000 FRBs a year. These are CHORD and the DSA 2000. One is based in Canada and one's based in the US. And each of these is going to see 10,000 FRBs a year, which I think will just improve our ability to understand these very strange cosmic flashes.
And how many are we seeing per year right now?
Oh, sorry. With CHIME, we're seeing about 1,000 per year.
Right,
And
right,
we're
right, right.
pinpointing probably 300 per year. Uh,
Okay. All right. Well, we'll keep a close eye on developments and hopefully you can come back, keep us up to date with whatever exciting new discovery is found. And if you, the audience, have any thoughts, please leave your comments and let us know what you think. But for now, thank you so much.
Thank you so much for having me, Phil. It was great talking to you.